Swayam Prabha. Digital India. Educated India.
Okay, so welcome back. Now, what we were doing last class was to sort of quantify the length scales, right, at which small scale turbulence is happening, right, and it's a small scale turbulence at which when we will have dissipation of energy, and that's what we looked at, and we saw that small scale turbulence at those length scales, right, this is basically proposed by Kolmogorov. So this is, it can be uniquely defined, right, with the dissipation rate, right, and viscosity. Okay, right. So now let me just what I will do now is kind of so we got these expressions, you see this one. So eta we wrote in terms of the Reynolds number, then this is the velocity, which again we wrote in terms of the Reynolds number, and then this is the time, right. So essentially essentially these are the relations, right, which we developed last time, and I can write these in this fashion as well. Right. So I can write it like this, and you can see that at large Reynolds numbers, right, as large Reynolds numbers, the eta, which is the length scale, u eta is the velocity, and tau is the time. So these all become smaller in comparison to the L naught, U naught, and tau naught, which are essentially the length, the velocity, and the time for eddies of the largest size, right. So now, having done this, so it's if I might sort of write that, okay. So that's my inference from here. So all of this, my inference is that at high Reynolds number, right, the scales of the smallest eddies, right, are small, compared to those of the largest eddies, right. So as you can see here from these relations here, so at large RE, right, at large Reynolds numbers, eta, u eta, tau eta, these are essentially length scales pertaining to small eddies, right. They are small compared to the length, velocity, and time of the largest eddies. So you can see that from here. So this is the relationship. Okay. Now, of course, this is from the numerics. You can see that. Another thing is that from flow visualization also, right, the ratio of say this the ratio of eta by L naught, which is flow visualization to show that when we increase RE, so as we keep increasing the Reynolds number, right, the size of the smallest eddies keep becoming smaller compared to the size of the largest eddies, right. So that's from flow visualization, right. That's also an inference. Let me write that down. Okay, this is essentially from flow visualization. Increase in RE. So, eta by L naught, right, decreases, right. This is from flow visualization. Okay. So, essentially what are we saying? Okay, that now so this eta, of course, it is a range, right. This is a range. So, we can say that if we find out the, if we say that for a given eddy, right, for a given eddy length scale, say L, right. So, let us just say this L, right. So, there is a length scale, right, which is higher than the smallest eddy size and smaller than the largest eddy size, right. So, this is a, you could write this as a range. So, if the range is such that it lies between this is a range, or this is the scale, So, the eddies which sort of lie in here, okay, so they are so essentially these are the small eddies that we are talking about. Okay. Now, at this point comes the second hypothesis. So, I am going to write that down. Okay. Now, I keep saying high Reynolds number. This is important. Okay. When I say high Reynolds number, okay, high Reynolds number, essentially what is Reynolds number? Reynolds number is V d by nu, right, or essentially velocity into characteristic length by viscosity, right. So, when I say that Reynolds number is very high, so high Reynolds number, what does this imply? That viscosity effects are small or negligible, depends on how high your Reynolds number is, right. So here basically we will say that when it is high Reynolds number, so viscosity effects are small, right. Depends on how you go to negligible, right. Now, earlier, right, when we developed these ratios, right, in the sense that when we developed these ratios, right, we said essentially that there is a certain length scale, right, where you can, in principle, these length scales can be uniquely defined using the dissipation rate and viscosity, right. So, now coming to this stage here where we are talking about high Reynolds number, and this is what we see. So, you can see that at very high Reynolds numbers, the scales are very small compared to the largest eddies, right. So, in this context comes the second hypothesis of Kolmogorov. So, so I'm going to write this down first. Okay. So, in every turbulent flow, at sufficiently high RE, the statistics of the motions of scale L in the range right, which we just said, have a universal form right, that is uniquely determined by epsilon, right. More importantly, independent of the viscosity, right. So, this is essentially the second hypothesis, right. Now, so having said that, so we've sort of looked at this length scale now. Okay. Now we're going to go a little further into this. Okay. So let's just say that let okay Okay, I'll explain what these mean. This di and all that. Okay, so right now just we'll just say we'll define a length which has some kind of subscript di. Okay, so let that be 60 times the smallest size. Okay, so and we then going to look at this length scale, right? Then I'm going to look at the length scale L, right. So, if you remember right, EI is basically 1/6 of the turbulent length scale, right. We were sort of we've done that earlier. Let me just cross check. Okay, yeah. So LEI was essentially 1/6 of L naught. So we said LEI is 1/6 of L naught, and L naught is the length scale, characteristic length of the largest eddy, right? Okay. So and we've defined LDI to be 60 times of eta, right? And we're taking some length between this DI and EI, right? So let me just write that down. So this is 60 times eta, right, and this is 1/6 of L naught. Okay, so we are looking at this. Okay, now so obviously you have the essence of defining these length scales is that I've been talking about this, I think the last couple of classes, is that there is energy, right, which is being transferred, right, and finally it reaches a length scale where there is no more transfer, right, and all this information as to how how the energy traveled, got transferred between one eddy to the other, how the eddies broke down, etc. All that information is lost, right? And all sorts of geometry information like mean velocity, mean central velocity, etc., etc. All that is also lost, right? But you come into this place now, which is unique, right? And you define at that place that there is no transfer of, there is no further transfer of energy; it's just dissipated, right? So, I have been talking about that. Now, obviously, so it's not, you reach the length scale and suddenly things start, instead of transferring, it's going to just dissipate. That's not going to happen, right? So, there is kind of going to be, it's going to happen gradually. Right. So, we are trying to define this range where there is the slow transition between, you have flow energy which is being transferred, and then it slowly moves into a length scale where there is no transfer, but there is just dissipation. Right. So, in the sense that you are readjusting, or you are sort of adjusting the sizes of or rather actually the eddies, the large eddies which are breaking down, and sort of they are kind of adjusting themselves, and bringing themselves into an equilibrium. Now, that's not going to happen like, off the cuff, but it's going to, sort of take its time and happen over a range of length scales, right? So that's why we are kind of looking, quantifying those length scales. So where is this happening, right? So, in that context, we are defining this DI and EI and things like that. Okay. So, another important thing that we are talking about here when we are defining the length scales is to the physical processes. What exactly are we looking at? So, here we are looking at the transfer of energy. So, we will also looking at energy when we are looking at the length scale, and of course, we are looking at the Reynolds number also to define these length scales, right. Okay. Now, so therefore, if I define it like this, right. So, the equilibrium range, right, where there is because the thing is that there is a large eddy and it's constantly breaking down. Does this constantly happen? No, it will stop after a while. Where will it stop? What condition would it have reached where it would stop? So, that is what we are trying to understand, that how small the eddy can get before this constant breaking down will stop. So, we are looking at an equilibrium range where all the eddies are now sort of in equilibrium, right. So, we write that net equilibrium range. So, net say net equilibrium range, right. So, I write it like this. So, L is less than this, right, and L is right. So, in here, so L is less than d I, which means that L is somewhere, the length scale is lesser than 60 eta. Okay. So, this is still small scale eddies, right. This is just that about 60 times, when the length scale is about 60 times the smallest of eddies, that is when this sort of range is happening. So, about that smallest eddy where it is about 60 times, this is dissipation is happening. This is the dissipation range, right. And when it is more than that, d I and this, when it is lying between this, when it is lying between this is called the inertial subrange. Yeah. So, this is the inertial subrange. So, we will keep discussing that. Let us see if we sort of I am going to discuss this further. So, see if we make some sense out of this. Okay. What does this mean? We have inertial, dissipation range, what is that and what is this inertial subrange? So, let us sort of define that a little bit. What is that? So, dissipation range is viscous effects are significant. Okay. So, here viscous effects right, viscous effects are significant, and here inertial subrange, right, the inertial effects are significant and viscous effects are negligible, right. So, here right, and viscous effects negligible. Okay. All right. So, I am going to sort of draw that scale. Let's sort of draw that scale again. Okay. So, what we are basically saying is, okay. So, right, this is the length scale of turbulent flow, okay, and this is the length scale of the smallest of eddies. Okay. Okay. Now, my L naught is 1/6. So, let my L naught be somewhere over here. So, let this is my say L naught. Okay. This is L naught, then I have a d I which is 60 times of eta. This is a L d I, right. This is 60 times of eta, right, and I also have L E I which is equal to 1/6 of L naught. This L naught is comparable to L plus. I think we have seen that. Okay. So, yeah, I guess I could write them closer to each other or something. Okay. So, this L naught is actually comparable to L plus. Okay. This is the largest eddy size. Okay. So, in that case, so I am going to sort of demark that. Okay. So, if I do that, so this essentially means so I am demarcating that. So, I have a range there, right. So, obviously, I mean, I think this, I mean, I do not think I have to reiterate this further, that we are marking these are just length scales. So, these are essentially eddy sizes in a log scale. Okay. Now, these are eddy sizes in a log scale. Now, obviously, when I am looking at a length scale which is just about here, it's in this range. So, there is going to be a gradual transformation or a transfer of the energy. Transformation also because whether it will break down or not happen, that is not going to sort of, this is not a strict boundary or solid boundary or anything. It is just more or less around that length scale, things are going to change, things are going to happen, right. That is what we mean. So far whatever we have learned is that now this is what is happening is you have this range, you have this range here L E I to this, right. So, this is where energy so, when energy enters the free stream, is basically enters into the free stream right here, right, into the turbulent flow. So, this energy is essentially contained by the larger eddies, but they are unstable and they are going to start breaking up. Okay. Now, once they start breaking up, then there must be, how long do they continue to do that? Well, they continue to do that till equilibrium is reached, where all the energy is redistributed, etc., and so the entire again you come to a position where so they start breaking down, energy is being transferred, and finally you reach a stage where energy is going to be dissipated, and this whole process where larger eddy is breaking down a small one will stop, right. So where is that? So this is that range where this is the entire, so this is okay. So now this one, when I say energy containing range, so this is the energy containing zone, and here this is the universal equilibrium range, right. So things are happening in this range where all the eddies are trying to come to reach equilibrium. Okay. So in that process, how the energy is being transferred, how the sizes are being adjusted is the processes which are happening. We're trying to kind of understand that. Okay. So this is the universal equilibrium range, and as we just said, that in this range, okay, this is still the inertial subrange, right, and this is the dissipation range. Okay. So that's why we're saying subrange, because this is the energy containing range. Here, the inertial forces are dominating, and dissipation range, essentially viscosity is dominating, but there is an inertial subrange where the viscosity is not yet negligible. Okay, it still has effects of that viscosity. I mean, yes. So yes, viscous effects are still, it's not exactly. They're still there. Okay, so that's why we say inertial subrange. Okay. Now then, having said that, so let's I'm going to write an inference here. Okay. Okay. So so I think. So energy containing zone, so bulk of the energy is contained there. I think that is fine. Okay. Now let us now sort of tell ourselves. I think you can see the meaning of EI and DI as I have written here, but let me write that down. Okay. So L of EI, essentially what I'm saying is, this is a demarcation between the energy and the inertial ranges, right. So this is a demarcation between energy and inertia ranges, right. Then another thing is DI. So you can see that is a demarcation between the dissipation and inertia ranges. Is that right? Now it's simple. So this is a demarcation between dissipation and inertia ranges, hence EI and DI. Okay. Okay. So I think we've sort of let us redefine the way we had come up with the eta, u eta, and tau eta for the small scale turbulence, right? Now, where we took both, where the dissipation rate as well as the viscosity into account, and we came up with those relationships. Now, then let's just say, given an eddy size L, right, in the inertial subrange. Right, characteristic scales are formed from epsilon and L, right. So, essentially okay. Okay. Then right, this is equal to okay. So, we get two scales here. Now, so again from the second hypothesis, using the second hypothesis, right, is that's what we're using here, that we're kind of ignoring viscosity, right, and we're ignoring the viscosity and then coming up with the scales for the velocity and time. So, then from the second hypothesis, so in the inertial subrange, right, the velocity and time scales, as you can see, right, they decrease, right, they decrease as L decreases. Yeah, I mean they vary similarly as the length scale, in the sense if L increases they increase, if L decreases they decrease. So essentially what I can say is here in the inertial subrange, okay, so the velocity and time scales decrease as L decreases. So, we can see that here, right. So, because here if you see UL, right, is directly proportional to L, right, and again tau L is directly proportional to L. So, if you so therefore so the velocity and time will decrease if L will decrease, or they will increase if the L increases. So, in other words, what does this mean? If L decreases, means as the eddies decrease their size, right, their corresponding velocities and time scales also decrease, right. That is what this means, that if the eddies decrease in size, then the corresponding velocities and times also decrease. Okay. So, in other words, so I might as well write that down, which is another way of looking at this. So, as the size of the eddies decrease, their corresponding velocities and time scales. Also decrease. Yeah? Okay. Okay, so now let us look at something else. Okay, so we've talked about length scales. We are now talking about the ranges of length scales. It defines what you have large eddies breaking down, which contain the maximum energy, and then they break down. Then all of these eddies, they try to gain equilibrium, right? So that is happening over a length scale, in which part of it is an inertial subrange where viscosity effects are negligible, whereas the other, it gets to a point where it's the smallest of the sizes, and there essentially it is viscosity is completely negligible, and the viscosity effects are not negligible, and dissipation is happening, right? So right. So now let's just say, now the question also arises that we're looking at time scales, right? How energy is being transferred and how it is changing in size. This length scale is essentially changing in size. The size of the eddies is changing. Now the point is, then how quickly or what is the rate at which this energy is being transferred? Is there a way to figure that out, right? So let's just say, right? Let's just say that this, right, is the rate of transfer of energy from a large eddy to a small one. So when I say that, I essentially mean that yeah, so we've looked at the length scale, so I think I don't need to specify this here. So when I said large eddy, so I'm looking at a length scale. So now you know which length scale to look at, right? So you will know which length scales to look at, right? So if you are here, you will know that around here there is transfer of energy, there is transfer of energy over here, here there is dissipation, right? So now we're talking about what is the rate of that transfer of energy, right? Okay. Okay. Now let's just say, now we know this now, right, is equal to, okay, and this is time okay. Now then square is equal to this yeah, so that, right? Now or we're trying to calculate the rate of transfer of energy, right? So this is kind of representing the energy, right? Now, so I'm dividing that by time, right? So that's going to give me the rate of transfer of energy. So this is going to be what? So this is epsilon square L square by L square epsilon 1 by 3. Okay. So what happens? Cancel out, and these two becomes epsilon to the power 3. So that this actually becomes epsilon, dissipation rate. is interesting, right? Now, this TL obviously is the rate of energy transfer is of the order, right, half mv square, okay, is of the order this. So, which is nothing but the dissipation rate. This is nothing but the dissipation rate. Okay. So if you look at this, right, so let me just go to the next one. So, this is the rate of energy transfer is equal to this. What are the inferences that I can make? Okay. What is the inferences that I can make? Okay. Right, is independent of the length, right, in the inertial subrange, right, is independent of L in the inertial subrange, right. Yeah, so it's rate of heat transfer, rate of energy transfer is equal to the dissipation rate. So again, I'm kind of repeating myself, but then we looked at pictures, right, right at the beginning as to how the turbulent flow looks like, for a jet, etc. So we had different sizes, and it was looking that there's nothing very orderly about this, right. So now we are at a state where we are trying to quantify that, that if it is this large, then what is the physical processes that's happening there. Yeah. So now mathematically, using some math, we've seen that actually the rate of heat energy transfer is equal to the dissipation rate in the inertial subrange. Okay. So I can sort of, let's just, yeah, so constant rate of this thing. So I think let's just go back to the slide here, to where we were doing this, right. So if we have this picture, let's sort of, so this is the, of course, dissipation rate, okay. Now, and so in transfer of energy to, so the rate of transfer, right, rate of transfer of energy rather is this. So constantly there is a transfer of energy from larger eddies to smaller eddies, right, in the inertial subrange. Okay. I'm going to write something here, and then we'll sort of describe that a little later on. Okay. So now here, okay, there is something called production, right, P. Okay. So something here that goes on kind of here. So there is this production P, which I'm going to just denote there, and there is basically, when I draw the arrow, I basically mean that energy is being transferred at this rate from larger sizes of eddies to the smaller ones. Okay. So now if you look at this, so this we said it is independent of L. Actually, we actually did say that it is independent of L. So although I'm writing here L, right. So now we did this, and we saw that it is actually just equal to the dissipation rate, and it is actually independent of L, right. But let's just say it's L, right. It's L here. So which means in this range there is the rate of energy transfer. So this T of L is basically T of L of EI, right, then T of L of DI as well, and which is equal to epsilon. So let's just sort of write that, see, or should I write it here. No, I think we can write that here. Let me write that here. Okay. Now, you see T of L, okay, is T of L of EI, right? And it is also, so T of L of EI, yeah, so TL, okay, is essentially this, right? And you can say that you can denote this as T of EI, that's okay, okay, and this is also equal to, right, this. However, this is equal to epsilon, which is the dissipation rate, right. So, let us just say I am going to write it here, this is equal to epsilon, which is constant rate of transfer of energy from larger to smaller eddies. Yeah, okay. I think we're a very good place to stop. Okay. So, what we've essentially, so this is the Kolmogorov length scales, right? We're sort of quantifying that. Okay. So, we basically said that we have, this turbulent flow, it has its own, it has its characteristic length which defines it, right? And the largest eddy sizes are comparable to that length, which I denote as L naught, right? Now, there is an energy which is, there is a sum total of energy which is being transferred obviously to this turbulent flow, which is, which is what it is doing is that this energy, when it enters into the turbulent flow, right. So, it ends up, so this larger eddies, right, end up breaking down into smaller ones, right, and this is a process which continues till we reach a range where this breaking up transfer of energy is not happening, it is just dissipating, right. And when that happens, it is basically, this is almost kind of a buffer zone where that transformation is happening, right. So, there is this, and in this inertial sub range, right, where there is a constant rate of transfer of the energy, right, and this is essentially equal to the dissipation rate. Okay. Then of course, when you come to dissipation rate, everything is dissipation. So, so that's what that's all I have to say about the length scales, right? Length scales, and in terms of what is a big eddy and what is a small eddy. I mean, how do you define what is big and what is small? So that's the kind of thing that we've discussed here, right? And in the process of describing this length scales, now how do we decide these length scales is how energy is being transferred, right? And that is also the size of the eddy is also related, or also depends on the way the energy is being transferred, right? In the sense that if you have very small eddies, there is dissipation happening. If you have slightly larger eddies, then you have energy is being transferred, and the eddies are also breaking down. Okay, so I think we'll stop here, and we are going to talk about some energy spectrum, etc., in the next class. Okay, thank you.